Alright, so this is going to kind of try to make learning a little bit easier, right? And trying to explain the PN Junction diode. Alright, so here I kind of depict attraction-free electrons. Okay, when we can see in the N-type and the P-type, where the P-type semiconductor material has silicon atoms doped with boron right in the center. Boron having normally 3 electrons in its valence shell, and on the N-type semiconductor we can see that silicon again is doped this time with phosphorus, which has 5 electrons in its valence shell. Again, we can see where an attraction occurs at the junction. Okay, that's that line going kind of through the center right there. We call it the junction barrier. And right here specifically, when this recombination occurs, we call that the depletion zone, where essentially the hole is switching places with the electron. But in reality, the hole actually never moves, right? The electron is just filling in the hole, the extra space that the silicon and boron have created when they have created their covalent bond. Okay? And this essentially creates a negative charge on the P-type and a positive charge on the N-type, right at depletion layer, depletion zone. Forward bias, we'll explain that for semiconductor theory, is when the battery is connected so its voltage opposes the junction field. So essentially what it's doing is, as it opposes the junction field, creating a smaller junction field, it reduces the junction barrier and essentially aids current flow. Okay, and this is done by placing the positive terminal of the battery or voltage source on the anode or the P-type side, and then a negative connection of the battery or the voltage source to the N-type or cathode side. Okay, and this is a depiction of essentially how the N-type has majority carriers of free electrons and the P-type has majority carriers holes. Okay, well, you can see right in the center, a narrow depletion region is created in forward bias. Okay, this is low resistance. In most semiconductors, silicon types will require about 0.7 volts in order to overcome this this depletion region. As the depletion region gets larger, we'll talk about that later, that occurs in reverse bias, and it's going to require a much more substantial amount of voltage to overcome that depletion region. So forward bias kind of continued is conduction by majority current carriers. Increasing the battery voltage will also increase the number of majority carriers at the junction and increase current flow. Now, understand that too much current will damage the junction, and we all know that heat is obviously created by current is a semiconductor's kind of worst enemy. So now reverse bias, okay, is actually obviously quite the opposite, where a battery is connected so that aids the junction, okay, and creates a large junction in that region. Okay, it increases the junction barrier, which obviously increases resistance to current flow. High resistance also creates heat, so remember that. Too much voltage, too much current will essentially damage that semiconductor. And you can see here where the depletion region has widened, okay, where essentially we have aided the depletion region by connecting the negative terminal of the battery to the P-type side and the positive terminal of the battery to the N-type side. So now the majority carriers on each side kind of start to flip-flop, okay, and eventually it'll fill conventionally, and you will not get a current flow. So this is probably the easiest way I thought of kind of driving this home and explaining it. Okay, I've got a bunch of frogs and lily pads. Okay, on the right side you will see that there's a lot of frogs, obviously filled lily pads. Okay, this is going to be my N-type side, where I have an excess of frogs. Okay, so remember that there are an equal number of protons and equal number of electrons on either side. Okay, which makes it electrically neutral. Okay, the division in the middle indicates the junction barrier. All right. On the left side, I have the P-type semiconductor, and that's going to be implied by the frogs on lily pad and then extra lily pads to show and depict that we have extra room essentially to be filled in those atoms, creating those covalent bonds. Okay? And remember that the ultimate goal of an atom, okay, is to reach, essentially it's nirvana, right? To reach the noble gas state, which has 8 electrons in its valence shell. Okay? And if we do some counting here, we understand that phosphorus and silicon on the right side, for example, will have 5 and 4. Obviously, that equals 9. So we kind of kick one of those electrons out in order to reach our nirvana state. So we're all in a very happy state. On the left side, quite the opposite has occurred, where boron and silicon are kind of dissatisfied and they still have room for one more electron to fill, so that way they can reach their nirvana state. Now, when you put these two materials together, and unfortunately, no, you just don't sandwich them together. They're actually grown. There's a process to it. What essentially happens is that these electrons have just enough energy as far as drift goes to kind of drift over here and fill those extra spaces. Okay, so now on the left side here, what we've done is essentially, remember that boron and silicon, for example, all right, have now, you've just kind of disturbed their equilibrium. Okay, so now we've added an extra electron to that atom, so unbalancing the proton to electron ratio. And on the right side, we've done the same thing, but of course opposite, where now we've taken an electron from the phosphorus. Okay, so now they still have 8 electrons in their shells. Okay, but there's now a difference in ratio. There are more protons than there are electrons. Okay, so this creates positive ions on the right side and negative ions on the left side. But what we have created is a state of equilibrium in this depletion region. Okay, we've depleted the number of free anything on either side. Okay, i.e. why it's called a depletion region. Okay, so in doing so, what I've created is an area where nothing can get through anymore, because now that these electrons have reached their state of nirvana, they've reached the noble gas state, they have 8 electrons in the valence shell, there's no reason for them to go anywhere. This depletion region will remain and will stay like that forever. This is a permanent thing. This is why it is a requirement, all right, in order for you to utilize a diode in forward bias. Okay, you have to kind of make a sacrifice, right? You have to give about 0.7 volts in order for the current to kind of bypass and jump over, essentially, this depletion region. Okay, that's the depletion region right there, which we created. Okay, now I want to talk about reverse bias first, because I think it's probably one of the most difficult things to grasp when it comes to speaking of PN junction diodes. Okay, so if I were to take my negative terminal of the battery or voltage source and connect it to the left side, which is my P or my anode side, okay, and I were to interject current, right? Because remember, understand that conventionally they say that electricity flows from, or current flows from positive to negative, but we know that electron flow actually indicates that it flows from negative to positive. Excuse me. So adding more electrons, or in this case frogs, okay, will essentially fill up all these lily pads. Filling up all the lily pads, again, what we're doing is essentially making this kind of equilibrium here kind of happy, right? So although we have negative ions now, we have introduced another electron to be added into that covalent bond, which essentially again creates a state of peace, nirvana, where I've reached my noble gas state. There's no reason for me to go anywhere. There's no reason for me to conduct. This is where I want to stay. And if you remember, back in the physics, all right, talking about atoms, and we talk about conductors, where conductors have anywhere between 1 to 3 electrons in their valence shell, which is what makes them conductors. Semiconductors have 4 electrons in their valence shell, and then insulators have anywhere between 5 and 8 electrons in their valence shell. And this is because the closer that they are to this noble gas state,